Hello friends, today we are going to study about integration and definite integrals. Now this topic of definite integral has got its origin and roots in a very old problem which was tackled by Archimedes. Now that problem was how to find area of a curved surface. Suppose I give you an ellipse or a circle or a parabola, how will you find area of that curved surface? Now Archimedes invented or devised a method called method of exhaustion. I will just briefly explain what this method means. Suppose I give you this circle. Now you have to find area of this circle and assume that you don't know the formula for area of a circle, which obviously Archimedes didn't know before this method. So what he did that, okay, let's say that, okay, I don't know area of circle, but I will approximate my circle with a triangle. Now if you are approximating this circle with triangle, you will get some answer, but that answer will be very crude answer. It will not be close to the correct answer. Why? Because we are losing out on these three areas. We are not counting these three white portion. Then Archimedes said that, okay, let's, instead of triangle, let's take a square. Then he found that, okay, his answer is much closer to the correct answer. Now if instead of say square you are taking a pentagon or a hexagon, as you go on increasing your number of sides of this regular polygon, what Archimedes found that, okay, this error, this white portion which was being left out, that white portion is being squeezed. They are decreasing in area. It means, so he thought that, okay, if I make a very large sided regular polygon, that if number of sides, that is the n, if it goes on increasing, then ultimately what will have, ultimately this circle, the area of this circle will be exhausted. Exhausted meaning the area of this circle will be completely covered by this regular polygon, which may be 100 sided regular polygon or 200 sided. So this is the method, that if I let my n tending to infinity, if my n becomes very large, then I can approximate a circle with an n-sided regular polygon. Now I have taken a circle here. Same process can be used for a parabola also, for an ellipse also, for any arbitrary shape. This was done by Archimedes. What is that? You take any kind of shape. The whole idea of this method of exhaustion is that you have to cover that shape with a known shape, like say rectangle or a square. I know the formula of area of rectangle. I know the formula of square. So what Archimedes did, he covered that arbitrary shape, which may be of any shape. He covered that area with a square or a rectangle. And now this method really works. I will show you. Suppose I have got a circle here. Now the radius of the circle is rr, so the angle contained is theta. Obviously this theta will be 2 pi by n. If this side is a side of n-sided regular polygon, then this is total angle is 2 pi. So this angle will be 2 pi by n. Now what will be the area of this triangle? I will use the formula, area is equal to half bc sine a. So this will be half r square sine theta, where theta is equal to 2 pi by n. So now this, see, the area of this circle will be n times the area of each triangle under the limit n tending to infinity, because when my number of sides of the polygon becomes very large, like this, then ultimately this polygon will completely cover my circle. So this area of circle will be limit n tending to infinity n times area of triangle. So this will be limit n tending to infinity n times half r square sine 2 pi by n. Just rearrange this term, like put pi here, put a pi here, this 2 will come to here and this n will come here, so you get this thing. Now you see, as n tends to infinity, what happens? This 2 pi by n will tend to 0. Now I can use this formula, limit x tending to 0, sin x by x is equal to 1. So this whole thing will go to 1. So I will get my area of circle as pi r square. This is a very simple derivation of area of circle using this method of exhaustion. I have used this for circle. Same method can be used for any kind of arbitrary curve. So suppose I have gotten this is y is equal to fx is an arbitrary curve. To cover this arbitrary curve with say known figure, so known figure I will use is rectangles. To cover this with rectangles, I have to divide, say, this x-axis from A to B. I have to divide it into different sub-intervals. So let's say that I am dividing into n subintervals, a is equal to x0, x1, x2, xn is equal to b. So this set is called a partition. So basically what I have done, I have partitioned my x-axis from a to b into n parts. The length of each part will be delta xk. Say suppose I have got a kth subinterval, so the length will be delta xk. Just to make my calculation simpler, I will assume that all these subintervals are of equal length, so that I don't have to worry about the length of the subinterval in each case. Now see what I have done here. I have divided my x is equal to a to x is equal to b, this x-axis into n different subintervals. The length of each subinterval I have taken as b minus a by n. I have assumed that all the subintervals are of equal length. This has been done just to make the calculation easier. You can assume that all the subintervals are of different length. There is no problem in that. Now I have made certain rectangles. Now if my main goal is to find the area of under this curve, area under this blue line between x-axis. Now if I approximate this area with the area of these rectangles, obviously you will get an approximate answer. That's what I have written here. A is approximately equal to Sn. Now what is Sn? You calculate the area of each rectangle and then add them. So that's what I have done here. K is equal to 1 to n, this is summation. Fck is the height of each rectangle. Suppose I am working in this kth subinterval. So height of this rectangle is Fck, width is delta xk. So this I have done Fck b minus a. So this I will get the total area of all the rectangles, the yellow ones and the blue ones. So and I am saying that okay, the total area of rectangles will be approximately equal to area under this curve. Now this is approximate. Now there is one problem. You can say which ck I should take in say kth interval. Now that's a very valid question. When I come to the next part, when I derive this formula, I will prove that okay, this choice of ck is immaterial. You will get the same answer. Suppose somebody is taking ck here, then what will happen? Suppose you take ck here, then your height will become like this, then your rectangle will be shorter. So that is, I will prove that the choice of ck is immaterial. Now why this area of rectangle, sum of the area of rectangle, that is Sn, this will not be equal to the exact area A, because you see in this particular this rectangle you are counting this extra area, you are leaving out this area. Again here you are leaving out these two white portions. So basically this is an approximate formula. But you get one visual appeal, you get one visual explanation that if I go on increasing my n, that is if I go on increasing the number of rectangles, then all these rectangles will start sitting on very, very tiny base. They will become very, very small. So what will happen? That these rectangles will very finally try to cover the curved surface, this curved y is equal to fx. In that case, what will happen? This error which I am getting right now, that error will be very, very small, and under the limiting process, that is limit n tends to infinity, this sum, that is Sn, will be equal to the exact area A. So this is my proposition. I will prove this right now, but I am giving you just a visual prelude, a visual explanation that why it should happen in the first place. Another very subtle point is that as I go on increasing number of these rectangles, that is as n tends to infinity, what happens to the delta x? That is delta x is b minus a by n, that will go on to become 0. No, not exactly 0, but very, very close to 0. So each of these rectangles are sitting on a base of very, very tiny width. So ultimately this thing fck into b minus a, each of them individually will be very, very close to 0, like something, they will be something like 10 to the power minus 12 or 10 to the power minus 16. I am just giving a rough approximate figure just to give you an idea. So you may say that how come if I am adding these very, very small rectangles, how I am getting an area A, which is a finite area. This curve may be having area of 10 meters square or 20 meters square. How come it happens that when I am adding very, very small rectangles, I am getting 10 or 20 as the answer? Now this is a very valid question, and this is the key point of both differential calculus also and integral calculus also. What is meant by infinitesimal and what is meant by infinite, and what happens when you multiply an infinitesimal with an infinite. I will give you a good analogy. Suppose I give you one sand particle. The mass or the weight of each sand particle will be very, very small, something like say 10 to the power minus 12 gram or minus 16 gram, or maybe more, 10 to the power minus 6 gram, whatever. So if I give you one sand particle, its mass is very, very small. But suppose if I give you one handful of sand, say one fistful of sand, that will have a finite mass, something like 10 gram or 15 gram or 20 gram. Now how does that happen? That happens because when I am giving you one handful of sand particles, I am giving you innumerable number of sand particles. I am giving you infinite, almost infinite number of sand particles. So each of the sand particles may be of very, very small weight, but when you add those very, very small weight infinite number of times, billions and billions times, you get something like 10 gram. The same thing happens here also. Each of these rectangles individually have very small area, but when you sum them over, 1 to n, and this n tends to infinity, that is n is something like billions and billions, ultimately they will give a finite result, say of 10 or 20 or 15 or 17. So this, the key idea is that when you are adding very, very small quantities, those quantities individually are as close to zero as you can say. That's the whole concept when we are dealing with differential calculus. That is the concept of dx. This dx is as close to zero as you can say. This is dx is almost equal to zero. Not exactly zero, but almost equal to zero. But even then, when you start adding these very many number of dx, you get a finite value. So this is the key idea here also. Now let's whatever I had derived by a visual explanation, let's derive this with a rigorous proof. Now suppose, let's concentrate ourselves on one of the particular subinterval, say this ith subinterval. In each subinterval, the function will be having a minimum value. I have denoted that by small mi, and the function will be having a maximum value mi. Now as I had told earlier also, that the area of this rectangle will obviously depend upon the height you are choosing. If you are choosing the minimum value as your height, you will get a smaller area, that is this is the green area. If you are choosing the maximum value of the function as your rectangle's height, you will get a larger area, that is Ri. So I can say that mi delta xi is less than ai is the exact area I intend to find, I have to find. So this mi delta xi will be less than ai, and this ai will be less than capital Mi delta xi. Why? Because in this red portion you are getting this red portion extra, so this is more. In this smaller mi you are leaving out this area, so this is less than the actual area. Now this is a very simple inequality. If you add this inequality for all the subintervals from 1 to n, what you will get? Summation I is equal to 1 to n, mi delta x will be this thing. Now since each of the inequalities, the individual, this is less than ai, if you add this side you will get the total exact area I am trying to find out. Now this sum is called lower sum ln. Now you can say why this n is sitting here. This n is sitting here because this lower sum is dependent upon n. If you take 10 intervals, you will get L10. If you get 15 subintervals, you will get L15, and I will prove it in next step. This L10 will not be equal to L15 because the number of subintervals are increasing or decreasing, that is they are changing. Similarly, I have defined upper sum as, if you take this capital Mi delta xi, you will get this sum. This will be greater than or equal to A because this individually each rectangle is greater than in area to this exact area ai. Now, so therefore I can say that ln is less than or equal to a, less than or equal to un for all n. This is very simple, that the lower sum has to be less than the exact area I am trying to find, and this area a has to be less than or equal to un, the upper sum. Lower has to be less than the exact, and exact has to be less than un. This is true for all n is equal to 10 or 20, whatever. Now you can say what will happen if I go on increasing my n. Suppose I have got say L10, now I have got L15. So what will happen? Whether they will increase or decrease. If I from L15 I go to say L27, then what will happen? I will prove right now that L10 will be less than or equal to L15. L15 will be less than or equal to L27. That is, all these L's will form a non-decreasing sequence. Non-decreasing meaning they can remain constant at one value, but or they can increase, but under no circumstance they are going to decrease. Similarly for UNs, I will show that this U10 will be greater than or equal to U15, or will be greater than or equal to U27 or anything. Meaning these U's will form a non-increasing sequence. So let's see how they function. This is the same thing I have written earlier, the same sequence I have written, that this will be basically I'm trying to write everything in mathematical jargon, so you may find it very intimidating, but don't be frightened by them. I will show you how these L's are forming a non-decreasing sequence. Suppose I have got an interval from 2 to 4. In this interval the mi, that is the minimum of the function, is 5. So what I will get my L, the contribution from this interval will be very simple, 5 into length of this interval 2, that is 10. Now suppose what I do, I subdivide this interval. That is the whole idea of taking limit and tending to infinity. When I subdivide it, say by here, this is my 3.3, what will happen? This 5 will be either here or here, maybe in one of them or maybe in two of them. Suppose they are in one of them. Suppose this 5 is here. Then when I am going to find out mi of this new subinterval, this mi, this minimum, has to be greater than 5. Why? Because when this whole interval was taken, this 5 was the minimum, meaning this 5 was minimum for the whole interval. Now when I am subdividing that interval into 2 parts or 4 parts, the new subinterval which I am creating will have a greater minimum value. Why? Because this 5 has already set a floor value. Nothing can go below this 5 in this subinterval. So 5 is telling that nobody can be less than me. If you want to have a minimum, you better be either equal to 5 or greater than 5. So suppose this is equal to say 7. So what will be now your new L? If you are increasing your L, so your new L will be 5 into 1 plus 7 into 1, because your interval is now of length 1, will be 12. So what has happened? Your L has increased from 10 to 12. If you are increasing your number of subintervals, my L has increased. This is very simple. Because L is increasing, because as you go on refining your partition, as you go on subdividing your partition into greater number of n, the new subinterval which are being created, they will have a minimum value which will be greater than the previous one. That is the whole idea. Similarly, what will happen with maximum? Suppose this is my interval 2 to 4. Maximum for this is 10. Now this guy 10 will say, suppose if you are dividing it further in say in 2 parts, no problem, but the new maximum has to be less than me. It cannot be greater than me. It can be, in worst case scenario, it can be as good as me, but it cannot exceed me. That's because I am the big boss sitting here. I am the big boss sitting at 10. So if you are creating a new interval, your new boss has to be something like 9 or 8 or 7, but under no circumstance it can go above me. That's the whole idea of this is like the global maximum. It is like the boss of this whole interval. So if you are subdividing it into a new interval, the new boss which will be created, the new mi, that has to be below this. So when it has to be below this, if you find your un, that un will decrease. So this is what I have written here in the mathematical jargon way, that ln will be less than or equal to ln plus a. This will be less than or equal to a, because all the ln's have to be less than a. No matter if you divide it into L100 or L200, ultimately they are lower sums, so they have to be less than a. Similarly, the uns, no matter if they divide it, you divide it into U100 or U200, ultimately they are the upper sums, so they have to be upper than a, they have to be more than a. So this is for all positive integer n and j. So if I write it, you can say that okay, L10 will be less than or equal to L17 will be less than or equal to A will be equal to U22 less than or equal to U12. So this is a very general formula that else will be, so I will write it in another way. Basically this says that these else will be an increasing sequence or non-decreasing sequence, because in some cases these ln's may remain as at a constant value. So basically what it says that as n increases, that is under the condition of limit n tending to infinity, these ln's will go on increasing like this. So my L10 will be here, my L15 will be here, L27 will be here, L205 will be here, they will go on increasing. Similarly, as n increases, these uns will go on decreasing. So my U10 will be here, U22 will be here, U305 will be here, then U417 will be here. So as you go on increasing your u's, they will go on decreasing. So this looks like a very peculiar kind of very interesting kind of picture, that all ln's are increasing, and we also know that they cannot increase beyond this a, because this thing has to follow. No matter how big this ln will become, ultimately it is a lower sum, it has to lie lower than a. Similarly, no matter how this un falls down to, ultimately this is a upper guy, this has to remain above a. So what is happening, this un, they are falling, but they cannot fall below a. So ultimately it appears that this un is approaching this a, the exact area. Similarly, this ln, this is increasing, but it cannot increase beyond a, it has to stop somewhere at a. So this ln is also approaching this a. So this is the whole idea of definite integral, that if you have got a function such that these ln's tend to a, these uns tend to a, and both are equal, then I will say that the function is integrable. Otherwise the function is not integrable. There may be some weird kind of functions in which this equality ln is equal to a is equal to un does not hold, and those are non-integrable function. But mostly at this level, at our level, most of the function we will be dealing are integrable. Ultimately their ln will tend to a, their un will tend to a. So this is the definition of whether a function is integrable or not. Another point I would like to stress here, that this ln will be less than or equal to um for any m or n. Suppose I take say L100, then this I am taking say U22. This L100 has to be less than U22, although this L100 would have increased a lot, but this is something like say this upper sums are elephant. No matter how big a dog becomes, that dog cannot overtake an elephant. Similarly, no matter how big this L guy becomes, it cannot reach this U guy. Similarly, this U elephant, even if an elephant is sitting, it will be higher than the dog. So even if this U guy has fallen a lot, it will still be above this L guy. So ultimately what will happen, this L will tend to a, this U will tend to a, and this is the definition of integral function. Some of you might recall that this definition of integral functions which you are using, it is quite similar to the definition of continuous function. How do you define a continuous function? A function is said to be continuous if say limit h tending to 0 f of c plus h, I am trying to define continuity at x is equal to c, is equal to fc is equal to limit h tending to 0 f of c minus h. So a function is continuous if the left hand limit, this is the left hand limit, is equal to the right hand limit. Similarly, a function is integrable if the lower sums, the ln's, they tend to a, the exact answer. Similarly, the upper sums, the uns, they tend to a. Now this ln is tending from below, this un is tending converging from above, and ultimately both will meet at a, and the function is said to integrable.